Welcome back to this session on advanced class relationship. Today we will explore how classes can build a meaningful and controlled relationships, whether it's sharing data, forming associations, or defining ownership structures among the objects. So in this session we will cover these topics as friend functions and friend class. We will see how certain non-member functions or other classes can access the private and protected member of the class when needed. Then we will see the association, aggregation and composition concepts, and finally we will also see and learn how lifetime and part whole relationships work. So by the end of this lecture you will have a clear conceptual and practical understanding of how advanced class relationships help us model real-world scenarios more effectively in C++. Let's begin with the first concept, friend functions and friend classes. So this topic deals with how a class can allow external functions or other classes to access its private or protected members in a controlled and intentional way. Let's now understand the need for friendship. In C++, the principle of encapsulation states that the data inside a class that are its private members should be hidden from the outside world. Only the class own member functions should directly manipulate the data. This is a good practice because it keeps your internal implementation safe from unintended changes. However, in some scenarios we came across functions or classes that need to work so closely that they need access to its private data. For example, a utility function that compares two objects might need to look inside both objects' private data. Or closely related classes such as car or an engine class might need to directly read or modify each other's internal attributes. So in such cases, we do not want to make everything public. That would obviously break the encapsulation concept or principle. So instead we use the concept of friend. Friend function is a non-member function that has been granted access to private and protected members of the class. In other words, it's not the part of the class, but the class trusts it enough to let it look inside its private data members. Here's how we declare a friend function. In this example, we have a class called box with private member variable named width. Normally, private members can only be accessed by other member functions of the same class. But here we have declared a non-member function called showWidth as a friend of the class. So by declaring it as a friend class inside the class definition, we have essentially told the compiler that this function is not the part of my class, but I trust it. It's allowed to see my private data. So even though showWidth is defined outside the class, it can access the private member width directly. When we call it from main, it works smoothly, printing the private data that would normally be inaccessible. So friend functions are useful when we need to perform operations involving multiple objects of the same or different classes, and the operation logically doesn't belong to any one class. We do not want to expose the private data publicly, so just for one or two helper functions. Let's see a more practical and realistic example. Here we have 2 point objects, each with private coordinates x and y. We have defined a non-member function called distance to calculate the distance between the 2 points. It uses standard Euclidean distance formula. Now notice that the distance function is not a member function of the point class, but because we declared it as a friend, it can directly access the private data members named x and y of both the point objects. Without this, we would have been forced to create getter function like getX, getY just to expose private data. That would clutter our class unnecessarily and also weakens the encapsulation. So a friend function gives us a clear and more controlled way to share access. Sometimes rather than giving special access to one function only, we need to give access to all the member functions of another class. That's where friend class concept comes in. When we declare one class as a friend of another, All the member functions of a friend class can access the private and protected members of the first class. In this code, we have two classes, engine and car. The engine class keeps its horsepower private. No one can directly see it from the outside. But since the car is declared as a friend class, every function in car automatically gains access to the private data of engine. This makes sense conceptually too. A car and engine works closely together in real life. A car must know its engine power to display or use it. So friend relationship helps us express that closeness in your code. Now that we have understand how the friend class works, let's take one step further. In the previous example, we declared car as a friend of engine and everything worked fine even though the car was defined later. But what happens when both the classes need to refer to each other? That's when we need something called a forward declaration. So in real life systems, classes often have two-way relationship. For example, car has an engine and an engine might also need to know about the car it belongs to. So each class wants to refer to the other. However, when we define one class before the another, the compiler doesn't know yet what the other class looks like. If we try to use it directly, the compiler will give us an error saying something like maybe unknown type name, car, or incomplete type name, or similar sort of errors. So to solve this, we use a forward declaration. That is a simple line that tells the compiler that a class exists even if we haven't defined it yet. So at the top, before defining engine, we write class car semicolon. So this is forward declaration. It tells the compiler that there will be a class car and I will define it later. Now the compiler knows the name car, but it doesn't know its structure yet, but it is just aware that it exists. Here notice that the engine class contains a pointer to a car static car PTR. We can only use a pointer or a reference to the class after a forward declaration because the compiler doesn't need to know how big the class is. It just need to know it's a valid type name. Here are some cautions. While friend functions are powerful, but they should be used carefully. Overusing friend functions or classes can severely break the principle of encapsulation and makes your program harder to maintain. So here are few guidelines. Use friendship only when necessary and logically from a design perspective. Avoid making entire classes friends unless the relationship is very tight. Prefer member functions or public interfaces whenever possible. We will see about abstract classes and interfaces in our next sessions. Think of a friend like we will dive into one of the most important and slightly tricky part of object-oriented programming, that is data type conversions and operator overloading. So C++ gives us a flexibility to convert between basic data types, user data types like classes, and even between two user-defined data types. Along with this, we will also revisit how operator overloading interacts with these conversions. So data type conversions occur when data from one type is transformed to another type. C++ handles many conversions automatically, but as a programmer, we also need to define our own conversions to make the objects behave more naturally. For example, allowing an integer to automatically become a custom class object or similar things like that. We can categorize the conversions into three broad scenarios. Number one is between the basic and user-defined types, and number two is between two user-defined types. So let's explore each one with examples. Let's start a conversion from a basic data type to a user-defined data type. In this example, we have a ratio class with two integer members, numerator and denominator. We define a constructor that takes an integer argument. So this constructor acts as a conversion constructor. It converts an integer into a ratio object. We call constructor and assign the value to $r, or even we can write it just as $r is equals to C. So the compiler automatically calls the constructor a parameterized constructor ratio int to perform the conversion. So the message conversion from basic to user defined data type occurred can be printed from inside the constructor to make this behavior visible. And this allows natural assignments like r is equals to c. We can write it like that. That turns integer into a class object seamlessly. Second case is the reverse, that is converting a user defined type back to a basic type. Here we have defined a conversion operator function using the syntax. So we have a syntax like we write our operator keyword, then int, and then a function starts. So this tells the compiler how to convert a ratio object to an integer object. When we write int numerator is equals to R, the compiler automatically calls operator int, extracting the numerator value. You can think of it as a user-defined casting operation that integrates your class smoothly with the built-in types. The third and final case is when we want to convert one user-defined type to another user-defined type. For instance, converting a polar coordinate with radius and angle to Cartesian coordinates with x and y. Here we have defined a conversion operator function inside the source class, that is polar in this case, that returns a target class called Cartesian. When we assign cart is equals to pol, the compiler automatically calls the conversion operator, performing the transformation from polar to Cartesian coordinates behind the scenes. So let's see it in action. When we create a polar object with radius 10 and angle 0.78 radians, now when we assign cart is equals to pol, the compiler automatically calls the operator Cartesian inside the polar, computes x and y, and returns a Cartesian object. This is a perfect demonstration of user-defined to user-defined type conversion, and it makes your code more readable, expressive, like native conversions. Now that we understand conversions, let's revisit operator overloading, especially how it can interact with different data types. Here we have overloaded the plus operator in two ways. One version takes another ratio object, allowing expressions like r1 plus r2, and the second versions take an integer, allowing expressions like r1 plus 2 or plus 3 and something like that. So both functions perform the addition differently depending upon the type of the operand. So this demonstrates the function overloading with operators. So C++ automatically picks the correct one at the runtime based on the data type of the right hand operand. So in the first expression, both the operands are ratio objects, so the first overload is called. In the second expression, we are adding an integer, so a second overload runs. So operator overloading allows the class to behave more naturally, just like as with the built-in data types like integer, double, and so on. We can even overload comparison operators like greater than for both integers and objects. If we compare r1 greater than 4, for example, the compiler calls the version that takes integer, and then if we compare r1 greater than r2, it calls the version that takes another ratio. This makes object comparison very intuitive and very flexible and very readable. Sometimes conversion operators work hand in hand with overloaded operators. In this case, the comparison 4 greater than r1 looks like an integer on the left and a ratio on the right. C++ looks for a conversion, that is, it calls the conversion operator to convert r1 into an integer and then performs the comparison with the 4 or integer 4. So this process is known as type promotion through conversion. Now we are going to examine three closely related patterns for modeling part-whole relationship, that are association, aggregation, and composition. These determine how objects connect and are crucially their lifetime and ownerships relate with each other. So let's start with a broader concept, that is association. It's about uses a relationship. Association simply means that one object knows about or uses another. There is no ownership implied, either the object can be created or destroyed independently. There is no ownership implied. uh, any of the object can be created or destroyed independently. For example, consider an example with a teacher and a student class. So a teacher can teach many students and a student can have many teachers. Next, aggregation. Aggregation implies ownership conceptually, but the parts can outlive the whole, often modeled with the whole holding pointers to externally owned parts. In aggregation, we have a has a relationship but with independent lifetime. Aggregation means whole references the parts but doesn't strictly own them. Then composition is the strongest relationship. If the whole is destroyed, parts are destroyed too. Association simply means that one object knows about or uses another. There is no ownership implied, either the object can be created or destroyed independently. For example, consider an example with a teacher and a student class. So a teacher can teach many students and a student can have many teachers. Teacher only uses pointer. It doesn't control the student's lifetime. The student may be created on stack or heap elsewhere. You use association when objects interact, but they shouldn't be managing each other. So the key point is that association is collaboration without ownership. In aggregation, we have a has a relationship but with independent lifetimes. For example, a team has players. Players can belong to different teams over the time and can exist if the team is deleted. So the team stores players pointers. These are non-knowing. Whoever created the player manages its lifetime. Deleting a team will not delete the player object because they continue to exist. That is where aggregation comes in. Key point is that aggregation means whole references the parts but doesn't strictly own them. So in this example that I discussed, the team is a whole and player is a part. Then composition is the strongest relationship. If the whole is destroyed, parts are destroyed too. For example, a house composed of rooms. So rooms do not make sense without the house that contains them. So this is a composition relationship. House stores the room objects by value. That means house destructs room instances itself. When the house is destroyed, its rooms vector is destroyed also, and each room destructor runs. So parts cannot exist independently. So in object-oriented programming, when we say that the two classes are related, it usually means one of the two things. Either one class contains another class as a data member, meaning an object of one class exists inside the other, or the one class uses object of another class as a parameter or a return type in its functions. So these are the two main ways relationships are implemented in C++. Either through composition or aggregation, that is the has a relationship that we just discussed, or interaction through methods, that is the simple association concept. So if a class A has an object B as a data member, for example, engine class and a car class, and in car class, car has an engine. So we created an object of engine as its data member. Then car and engine are in a part-whole relationship. The nature of that relationship, whether it is composition or aggregation, depends on how the part is created and destroyed. So now that we have learned the basic difference between the association, aggregation, composition, let's dive deeper into lifetime or life or death relationships between the objects. We will explore when parts are created and destroyed, who owns whom, what makes a relationship a true composition or an aggregation. So let's start with the composition, the strongest form of ownership. In composition relationship, part is literally a part of the whole. The part cannot belong to more than one whole, and part's lifetime is managed entirely by the whole. So this is very important. When the whole dies, the part dies also. This is why composition is often called death relationship. A great real world example is a person and their heart. Heart belongs to exactly one person. So when a person dies, their heart also ceases to function as they are part of that person. So the person's body controls the creation and destruction of the heart, just as an object controlled its component parts in C++. So let's walk through this code. The heart class has simple messages in its constructor and destructor. Person class contains a heart object directly by value. This means a person who owns its heart. When we run this program, the heart is automatically created when the person is created. Person calls heart.beat, showing a normal use. When a person object P goes out of scope or it is destroyed, then the heart also dies automatically. The destructor order shows this clearly. First the person is destroyed, then the composed heart is destroyed. So this perfectly demonstrates a composition, a one-to-one ownership, a shared lifetime, and a parts destruction depending on the whole. Now let's look at aggregation. An aggregation is still a part-whole relationship, but with a looser coupling, you can say, not a strict one as we have seen in composition. So in aggregation, the part belongs to the whole, but it's not owned by the whole. This is important. The parts although belongs to the whole, but is not owned by it. The part can be shared between several whole objects, and most importantly, the whole is not responsible for creating and destroying the part. In short, aggregation is just like saying, I use you, but I don't own you. A perfect example is a student and department class. A student can belong to one or more departments, like computer science, mathematics. If one department is closed, the student still exists and can belong to another department. So now let's examine this aggregation example. The student class represents individual students. The department class holds pointer to the student object, but it doesn't own them. Notice how a department doesn't create or delete any student object. In main, we create two students, Alice and Bob. Then we create two departments, computer science and mathematics. Alice is added to both departments, showing that a single student object can belong to more than one department at once. Each department just keeps a reference or a pointer to the student. It doesn't manage their lifetime. So if a department was deleted, the student would still exist unaffected, and that is the aggregation. So the death depends on how you have implemented it. Maybe if you have implemented it like in destructor of whole, you are also controlling the lifetime of the part, then it's composition. And maybe in the similar scenario, but you have implemented it in a way that in the destructor of the whole, you are not controlling the lifetime of a part, then it's maybe an aggregation. So that entirely depends how you implement your lifetime, especially the lifetime, as I've already discussed, the lifetime is controlled by the constructor and destructors. So that is the core idea. That is how you implement the destructor, and constructors define whether you have implemented it as a composition or implemented it as a aggregation. So to wrap up, composition expresses total ownership. Parts live and die with the whole, and aggregation expresses shared or external ownership, that is, parts live independently. Thinking in terms of lifetime and responsibility helps you to design error-free systems. So whenever you design classes, ask yourself, should destroying the whole destroy its parts? So your answer determines whether you are going to composition or implementing it through aggregation. Thank you for staying with me through this session on advanced class relationships. We have explored how classes can interact with each other in powerful ways. So now as we move forward, we will step into next major concept in object-oriented programming, that is inheritance and polymorphism.